Hey everyone, my name is Shreyas. I'm a postdoc at Harvard. I want to talk about some very cool work we've been doing with Wayfair. This is joint work with Chris Ferreira, who's a faculty member at HBS, and Sunanda Parthasarathy, who's an associate director of data science at Wayfair. The problem that I want to talk about today is pretty simple. How should an e-commerce platform rank products on its web page? Nothing fancy about it so far. And the reason this belongs in an information design workshop is that people on the internet have unlimited patience and they want to look at everything you throw at them. No, I'm just kidding. People on the internet have a very short attention span. So really what rank that you choose, the ranking of products that you choose determines what they see. And you get to affect purchase decisions by controlling the information that people see. This is not a particularly new problem. So let me kind of motivate it with a slightly different setup than the kind of problems you'd see usually. The platform that we work with is Wayfair. Wayfair, if you have not heard of it before, it's kind of like Amazon, but mostly for home goods. Like Amazon, Wayfair, people go on Wayfair, they search and purchase products. But Wayfair also has these themed events, which are somewhat different. I guess you can't read very clearly on the screen, but essentially, each event is like a short sale. It has a finite collection assortment of products that are chosen beforehand. The prices are fixed beforehand, they're usually on sale. And the only thing that we can do is kind of affect the ranking of products within this event. These events are kind of all over the place. Some of them are pretty specific, like rugs that you see here. Some of them are kind of pretty generic, like Halloween events or like pet crates or something like that, budget-friendly sectionals. Why is this an interesting setting? Well, like I mentioned, the customers who come on this platform, come for these events, don't really know what the products are beforehand. So the platform needs to select a good enough ranking to get their attention fast. That's kind of the main challenge here. And if people don't like what they see, they're going to leave very soon. The other things that make this challenging is that the users who come to these events are usually first-timers or people who haven't engaged with the platform as much. So the platform or we, the algorithm designers, don't know what their preferences are beforehand. Finally, these events are short-lived. So in the previous page, most of these events were under a week. You can see the ends in 5 days, ends in, I guess you can't see the screen. So the mechanism that we design has to converge to an optimal ranking. It has to learn what the preferences of users are, and it has to converge pretty fast because the events are short-lived. That's kind of the challenge we're facing here. Let me dive right into the model. You have a bunch of customers and you have a bunch of products. Each customer has two parameters, a vector of click probabilities and an attention window. The customer's behavior is going to be as follows. The platform shows the customer a ranking pie. Now, initially, the customer is neutral about the event. So they're going to go through products 1 through K. Remember that K can be different for different customers. Now, as long as they're neutral, they're going to click on each product that they see within the top attention window with probability PIT, where I is the product and T is the customer. If you don't even elicit a single click from them within your attention window, the customer decides that the event is not for them, so they quit. And we say that this customer is not hooked. If the customer likes at least one event within the attention window and clicks on it, the customer is hooked, in which case we impose no restrictions on their behavior. So a hooked customer can go on clicking lots of products, can stay for longer than KT, and so on. No assumptions on that here. The couple of interesting things here that I want you guys to note here is that the attention window is different for different users, and the attention window is correlated with the preferences. So the reasoning for this is think of someone like a mobile user. These users tend to be young, and this affects both the products they like and their attention spans because they have short attention spans. Or we presume they do. Let me run through a very, very quick example. This is super deterministic, so all the probabilities are 0 or 1. You have exactly two products. This one is ranked 1, this one is ranked 2. You have 3 users. these guys have an attention window of 2. This person has an attention window of 1. So what happens on the platform is that the first 2 people come. The product that they like is ranked 1. That's great. They click on the product. You're hooked. Platform wins. Unfortunately, look at the third user. This person comes on the platform. The product that they like is at position 2, but their attention window is only 1. So the first product that they see is going to be this one. They think, oh man, maybe this event is not so hot, and they leave the platform and they're not hooked. Now, if you're paying attention, you can very easily see that if I swap the order, I can hook all 3 users at the same time. But if you look at just popularity metrics, this product is the most popular one because it appeals to 2/3 of your user base. So the kind of easy takeaway here is that ordering products by their popularity or their click probability is suboptimal. Hopefully the setting, everyone's okay with the setting. Our goal here is the following. You have customers arrive sequentially. The platform needs to select a ranking for each customer, and our goal is to maximize the number of hooked customers. Remember that a customer is hooked if they click on 1 or more products and they like the event. So maximizing the number of hooked customers is equivalent to minimizing the number of people who abandon the event because they didn't like what they see. If everyone's okay with this objective, we know that the ranking by popularity does not work. So what kind of algorithm does work? Let's start a little bit naive, and then let's kind of dive into the actual algorithm. So let's fix products sequentially in ranks 1 through n. So let's say that at this point, you've fixed products at ranks 1, 2, and 3. And you're deciding which product to have in rank 4. Now, you have 3 choices, product 1, 2, and 3. The naive idea is that you try all 3 of them in rank 4, and you pick the best one. And it's a greedy algorithm, basically. So you pick the one that kind of maximizes the marginal utility at this position. This algorithm does okay, but unfortunately, it's too slow. And like I mentioned, we need some fast approach. So we're going to combine this naive, greedy approach with some sort of threshold-based stopping criteria. The kind. This gives you a 1/2 approximation if the preferences are correlated, and 1 - 1 over E if they're independent. So we're going to try something a little bit more clever. We're going to fix a threshold tau. Instead of trying all the products, I'm going to scan through the products in some predetermined clever order. And the first time I hit a product that hooks at least tau users or has a click probability, marginal utility of tau, I'm going to fix that here. And then I move on to the next position. The advantage of this compared to the naive algorithm is that I don't have to try all the products in this position. Instead, in one pass through this, to the list of products, I can fix multiple ranks. So see what happens. Like, if I go through this product and this product, I can fix this one here. And then I try this one for rank 5, and I fix it here. So this offers quite the speed up compared to your naive greedy algorithm. Let me just quickly sum up what the result is. Essentially, this converges reasonably fast. It gives you a 1/2 approximation plus an alpha factor if the preferences and attention spans are correlated. And if they're independent, this improves to 1 - 1 over E. We have a lot of other cool algorithms in the paper, so you guys can go check it out. Let me spend like 1 minute talking about the data analysis part, because this was pretty challenging. So we came up with an algorithm. We wanted to test it. Wayfair gave us access to your data. Everything is great. Unfortunately, the problem was that this was click data. So all we had was you have historical events, and you have all the products that people clicked on. Now, how on earth do you infer customer preferences from this click data? Because if you want to test the algorithm, you need to infer what the preferences are. And if the economists in the room have a cool answer to this, I'd be happy to hear them. But we tried something that's fairly simple. We essentially did some sort of a Bayesian inference to map each user with 0 clicks to a preference profile of a clicked user. And the algorithm actually did OK in practice. We got anywhere between 5 and 30% improvement. OK, to sum up, people on the internet are like bored teenagers, and we came up with shiny toys to kind of get them hooked on the platform. The other, I think, main insight is that a lot of these learning to rank literature, for people who are familiar, proposes ranking products by their intrinsic popularity or click probabilities. This may not necessarily be a good approach if your customer base is heterogeneous or if they have short attention spans. So that's something to keep in mind. We tried more rigorous simulation methods, but I think if people have an idea on how to use click data to come up with customer preferences, I'd love to hear them. Thank you.
Speak first, Chris.
Okay, thank you everyone for staying till late, and thank you for the invitation. I'm Krishnamurthy Iyer. I'm at the University of Minnesota, and this is joint work with two students, Jerry Anunraj Wong, who was an undergraduate last year and is applying for PhD this year, and David Lingenbrink, who was a PhD student at Cornell and has graduated. So I'm going to talk about information design with risk-conscious agents, and I need to specify what I mean by that. So before I do that, let me start off with a very standard framework for Bayesian persuasion. So the typical assumption here is that there is some unknown state of the world, which let's call it omega, right? And there is a receiver, and the assumption is the receiver is Bayesian and expected utility maximizer, has some prior about omega, right, and must choose an action A, right? And there is a sender who observes omega, right, and shares information about omega to the receiver before the receiver chooses their action, right? And once the receiver gets the information, they update their belief according to Bayes' rule and choose an optimal action subsequent to that. And the goal of the sender is to maximize the expected utility, their own expected utility, which depends on the unknown state of the world, as well as the action chosen by the receiver, right? So from a practical standpoint, the thing to consider here would be a sender is a platform, and a receiver is a user or a customer, and the unknown state of the world could be, let's say, the congestion or the waiting time, things like that, right? And the sender's goal might be to get the receiver to avail the service, right? So what we do in our work is basically relax this assumption that the receiver is an expected utility maximizer. And for lack of a better term, I'm going to call them risk conscious, but if there are any better terms, I don't want to call them non-expected utility maximizer again and again, so I'm just calling them risk conscious. And what do I mean by a risk conscious agent? So let's just think about this. So suppose the unknown state can take one of three values, and this triangle denotes the probability simplex, right? And this is every point here is a belief of the receiver. And the expected utility maximizers basically says that utility is linear in your belief, right? So in particular, I denote the indifference curves, and these are all hyperplanes, right? And the risk conscious agent basically says that the utility could be any nonlinear function of their belief, right? So no restriction, pretty general, right? And what are the motivation? We have already seen a lot of talk today that basically talk about extensive empirical evidence that human behavior is not adequately explained by expected utility maximization, and especially when it comes to like these service systems where the customers are basically deciding whether to wait for service. It is known from literature on psychology of waiting that customers typically perceive uncertain wait times to be longer than definite wait times, right? And this suggests that the variance of the wait time impacts their decision whether to avail service or not. And variance is something that can't be incorporated into the expected utility framework. Right? Another motivation that we have for studying this is that a receiver could not just be one single agent, but they could be a group of agents, and their behavior comes out of some equilibrium behavior, for example, right? And in that case, assuming that they are an expected utility maximizer is not the right thing to do, right? So the question that we have is that what are the implications here for information design when the receiver is not an expected utility maximizer, right? To talk about that, let me briefly go over how the analysis works for expected utility maximizers. So one of the first step that one needs to do is to identify the signals that need to be sent to the receiver by the sender. What is the optimal set of signals, right? And the argument goes through basically through a revelation principle style argument, right? So let's say again we have the space of beliefs, and suppose the receiver has to choose one of two actions, right? And suppose all the blue lines are beliefs that induce the optimal action to be 1, and the red ones are the optimal action to be 0. And the argument goes that if there are two signals that the sender sends for which the receiver's optimal action is 1, right? If they just reveal that the signal is one of S1, S2, instead of telling which one it is, right? The receiver's belief would be something on the line joining the two induced beliefs, right? This is just Bayes' rule, property of Bayes' rule. So basically coalescing signals like this does not change the optimal action, right? So what you can do is coalesce all signals that lead to the same optimal action into a single action recommendation. Just tell people, oh, choose this action and choose that action, right? So this helps quite a bit in specifically, all you need is one signal per action in this case, right? And in fact, you can use this to show that the sender's problem reduces to a linear program with some obedience constraint that basically say that whenever I'm supposed to tell you to choose action A, it is in your interest to choose action A. Does that make sense? So let's see what happens with risk-conscious agents, right? It's pretty easy to say. So suppose I have two signals, S1 and S2, that induce beliefs denoted here, for which the optimal action is 1, right? And if I just coalesced these two signals, it could happen that the belief ends up in the red region, right? So your optimal action changes, right? So in particular, coalescing a signal can change the optimal action, and that's obvious because if you care about uncertainty and variance, if I reveal less information, your variance goes up, and you may no longer want to choose the same action. Right? So basically, the revelation principle fails. In particular, this implies that the action recommendations are no longer enough, and we don't have an LP formulation to find the optimal signaling mechanism. So it's unclear what to do. Right? So basically, the questions that posed now are like, how does one find the optimal signaling mechanism in this setting? And in particular, how many signals are needed in this case, right? And I won't have time to go into all the technical details here, but the main contribution that we do is we show that in this case, the optimal signaling mechanism can be found from a convex program, right? And at most, the state space number of signals are needed per action, typically much less than this. But this is the main thing. And I won't go into the details of the proof, but for those who are familiar with the concavification approach, we basically, instead of optimizing over the distribution over beliefs, we optimize over the distribution means, and that basically gives a convex program here, right? So the special case that we look at is what is called the binary persuasion, where the receiver just has to choose action 0 or 1, right? So typically think of this as like a buy, don't buy, or wait, don't wait, right? And the sender prefers always action 1 over action 0, right? So sender always prefers that the receiver buys the product or waits for the service, no matter what the state of the system is, right? And we assume here that the receiver's utility is convex in their belief. So this is a pretty mild assumption. And in this case, we can actually show that we do get back a linear programming formulation, like in the expected utility maximizing case. And in particular, we show that there is a canonical construction for the set of signals, right? In particular, in the optimal signaling mechanism, you will either reveal the entire state, or you will induce beliefs between two states, right? So just to give an example, so consider this where customers have to decide whether to wait in a queue for service or not, and their utility is something that depends on their expected value and the standard deviation of the waiting time, right? And the service provider is providing the queue length information, right? So in this case, we can show that the optimal signaling mechanism, for example, will require 6 different signals that will induce the join action, optimal action, and 1 signal that will induce the leave action, right? So you need to cut these different signals here. I'm denoting in different colors. Basically, this means that if the queue length is 2 with probability half, tell the receiver, I don't know, magenta versus brown, something like that, right? And so on. So with this, I'll stop here, and yeah, the paper is on SSR. Yeah. Thank you so much.
Next speaker is Mariann.
Okay, this is written down. Yeah. Hi, my name is Mariann Ollar, and I'm from University of Edinburgh. And today I'm an economist, and I work on mechanism design. So I will talk about the role of beliefs in transfer design. That's my main topic. And so just to give you the notations and also some primer thoughts about what mechanism design is all about. One way to think about mechanism design is that it is the engineering side of game theory. There is typically a hypothetical or an actual designer assumed in these problems who has a certain social goal in his mind. This can be optimal revenues, this can be efficient implementation. For now, let's just say that this social goal is given by a function f, which maps the state of uncertainty into an allocation x. Now, typically in a mechanism design environment, there are multiple agents whose preferences may depend on their own private information, theta I, but it may also depend on private information of other agents. And this is what eventually gives the valuation over the allocation that is given by the social goal too. Now, in these environments, in mechanism design environments, especially with private information, that is with incomplete information, it is very important what the designer knows about agents' beliefs. Now, beliefs are a way to describe what each agent knows about others' valuations and what he thinks those other agents would think about his valuations and private information too. Now, the typical modeling assumption in mechanism design with incomplete information is that we model these beliefs by a single joint distribution over opponents' types, which is a different way of saying it is that it's a subjective probability distribution given and known to the designer and commonly known to the agents. Now, this is the classic modeling framework, and it is known that many of the implementation results are very sensitive to this common prior assumption, these common knowledge assumptions. And so what we do in our papers with my co-author Antonio Penta is to take a different modeling approach to beliefs, and instead of fixing a single subjective prior for each type of each agent, we fix a set of possible joint distributions over opponents' types. This way, giving a more flexible, more various possible way of modeling beliefs. Now, classic mechanism design environments, as described in this abstract formulation, can be easily mapped to more practical problems which obviously include, as we have heard many talks today, and yes, and we will hear more tomorrow too, include auctions, taxations, public good provision. And in all of these problems, what's very important to notice is that the main issue for the designer is an informational problem. The designer would love to know all this private information held by the agents, and if he would know that information, then he would easily be able to set the social goal. But because he doesn't know that information, the first order task of the designer is to incentivize, to create a mechanism, create a game environment in which agents can truthfully reveal this information, or at least behave based on this information. So the way to describe, or the way economists say this, is that in a transfer design environment, when we look into direct mechanisms, the designer needs to make sure that incentive compatibility would hold. Now, as Shengwu mentioned yesterday too, incentive compatibility basically in a transfer design environment pins down the implementing transfer schemes. And this formulation that I'm describing here is probably many of you already know and are familiar with from the auction theory literature, but it easily and straightforwardly extends to arbitrary social choice functions, to arbitrary environments with possibly interdependent valuations. And it is just stating that ex post incentive compatibility, which is the relevant notion for belief-free implementation, requires using these very particular, uniquely determined transfers, which mirror the valuation functions and basically compensate back for the term that was depending on the true theta I type instead of theta I being a report there in the valuation function. Now, what we find in our papers is that under this rich model of belief restrictions, the corresponding notion, B incentive compatibility, requires similarly fixed transfer schemes, but gives a little bit more flexibility to the designer. So it's still the case that the incentive compatible transfers cannot be very different from the well-known ex post incentive compatible transfers. However, there could be an extra term. It must be an additive modification of the original ex post incentive compatible transfers. But this additive modification necessarily must be a belief-based term, which means that this KI function at the truth-telling profile for every possible belief of agent I with type theta I must be 0. So this is, if you try to think about it, is kind of instructive in multiple ways. One is that it shows us that with some information about beliefs, which is more informative than no information about beliefs whatsoever, it may be the case that there are more interim incentive compatible transfer schemes than ex post incentive compatible transfer schemes. And how many more of these ex post interim incentive compatible transfer schemes the designer can have access to depends on how much information he has about the beliefs of the agents. Now, it is very clear that in this setup, the smaller these B sets are, the more information the designer has about agents' beliefs. And the smaller these B sets are, the fewer of these conditions, the easier it is for these conditions to be satisfied. Therefore, it is likely that you can find more KI functions which satisfy these condition for a belief-based term. So I just wanted to highlight this, that the more restrictive B is, the more belief-based terms are available for the designer to use in order to shape the transfers. And these belief-based modifications can be useful for budget balance, surplus extraction, sampling for better revenue, And what we do in our papers, we use these belief-based modifications for full implementation. In the first paper, we find conditions under which one can eliminate strategic externalities and thereby guarantee full implementation. I'm just giving you these words to advertise the papers. I hope you will be intrigued to look into them. And in a second new paper for which we have the draft available already, we look into the assumption of identical but unknown distributions. And we find that even there you can find belief-based terms to achieve full implementation, whereas you couldn't, the designer couldn't possibly find implementing mechanisms which would achieve full implementation without that information of identicality of arguments. And so there are maybe two more cute results that I wanted to highlight. One of them is that this belief-based modification can be quite robust. In fact, many of our suggested implementations and transfer designs, it is the case that even if this KI function, the condition only holds approximately. So the expected value of this KI function at the truth-telling profile is not necessarily known to be a 0, but it falls within a small interval close to 0. Then the resulting implementing transfers still elicit a nearby type. So that's one of the sort of interesting results that you can already read in the published paper. And one of the other interesting results is that under identical but unknown distributions, we are able to characterize the full set of KI functions which are available for the designer to do these transfer modifications. And because we have this full characterization, we can study different notions of robustness. And what we find interestingly is that for different notions of robustness, one of them is robustness to limited depths of reasoning. Another one which we consider is robustness to mistakes in play. Different robustness notions will call for different implementations and different transfer designs. And I would leave this result on your mind, and please do ask me if you have questions about these two papers, because I'm really happy to talk about them.
Thank you very much. I think, afterwards we can have discussions outside, so I think there's, of course, a need for some people to ask questions, and I'm sorry that we don't have the time here, but I think all the speakers will be around for some time afterwards. Okay.
So my name is Francis Bloch, and I'm an economist from Paris, and I'm specializing these days on social networks. So this is going to be a paper about social networks, and this is joint work with my student Shaden Shabayek. So I'll try to look at Dorothea and stay during the 10 minutes. So the point of the paper is basically to try and see what happens when you have a planner. And the objective of the planner is to target agents in a social network. So what I mean by targeting can be different things. So one interpretation, for example, is that agents, what the social network describes, are synergies in the efforts that the agents are going to provide. So if I provide some effort and my neighbor provides some effort as well, then this is going to increase the amount of the output that we can create. So that's one example. A second example, and that's there I refer to work that I've done in the past and Ozan has done in the past too, is the idea that you have consumption externalities among agents. So some agents benefit from the fact that other agents consume the same good. So one example that you can think about is an influencer on a YouTube video who's going to give his dog a particular type of dog food. And then everybody else is going to look at that influencer and do the same thing. So that's another example of influence, and price discrimination then is going to be what agents want to do in the network. So when people started looking at that, they looked at it in a context in which the network was known. And recently, people have started asking questions, how can you do that type of targeting or discrimination if you only know part of the network? And what we're looking at in this paper is actually a very particular, very specific type of incomplete information you have about the network. It's the idea that you have access to the architecture of the network in the form of anonymous information. So what you know is, for example, that the network is a star, but you don't know which agent, what the location of agents in the network is going to be. So you don't know which of the agents is at the hub of the star, which of the agents are peripheral agents in the star, and so on. So think about it as an extreme version of privacy restrictions, where the only information you can have access to is an information which is totally without the names of anybody. And the question we ask in that paper is, suppose that actually you only have access to those restricted information, how is that going to affect your ability to target or to price discriminate in the network? Okay. So unfortunately, we do it in a very specific model, but it's a workhorse for many people who have been working on those targeting in networks model. It's a model where agents have that type of utility. So the first terms, forget about it. I mean, those are terms that we need in order to have linear best response functions. The last term is the interesting one. It's the term which captures the externality. So Gij means that there is a link between I and j. It's a directed link, actually, in our framework. And then Xi, Xj means that you have some complementarity in the efforts which are made by the two agents or in the consumption of the two agents. Now, it's well known that, it's not only well known, it's very easy to compute what the solution here is going to be. The solution actually is going to depend on the matrix G plus GT, where G is the adjacency matrix of the graph. So in particular, notice one thing, which is that we have GT here because you create externalities on the others, and the planner is actually going to want to increase the amount that you consume or the amount of effort that you put in order to make sure that you have those positive externalities. So in particular, notice one thing, which is that the planner is always going to ask you to do more than what the private agents would like to do. Okay. As I said, the planner only sees the network architecture. The agents, for the most part, only know their location in the network. I won't have time to talk about it, but I can talk about it offline, what happens if they know more. And the planner wants to elicit from the agents information about their location. So that's the novel part of the paper, is that you're going to have that mechanism where you try to have the agents explain what they have and, give you the information about the location. You can think about it as you have locations in the network, and you can offer a menu of contracts where XL is going to correspond to the contract for the agent located at L. And agents choose among that menu of contracts, and let's say that if two agents ask for the same menu, you realize that something is wrong. It could not be that actually two agents are at the same location, so then you can punish them. That's going to be, in fact, what you're doing here is that you're using the correlation among agents types to punish them as you would do in a Kramer-MacLean type mechanism. Okay, so think about that. The paper is more general, but think about that as the mechanism that we use to implement is just going to be that menu of contracts that people can choose from. Okay. First, incentive compatibility means that actually you choose the right location And the first proposition, it's a no-starter, because actually any contract that you can offer is going to be ex-post incentive compatible here. And the reason for that is just that you can punish agents from lying, and because you have correlation, no two agents can be in the same location. So you can immediately, if you look at ex-post incentive compatibility, then clearly, so that's not what you want. So let me move one step further and think about agents jointly deviating. So think about agents jointly misreporting. One thing I can do is basically I can exchange with one of you, pretend that I'm at the location of one of you, and vice versa. And now this is actually potentially more interesting. The reason why it's potentially more interesting is that you have a misalignment between the social and the private incentives. The agents would not want actually to, they do not want to make too much effort, and the planner forces you to make a lot of effort. Now, again, this is a non-starter because for reasons that I can explain offline, the optimal contract, the G star that you can choose, is actually going to be group incentive compatible, at least for groups of size 2 or 3. We don't know for 4 and more, but we suspect that actually it's the same for 4 and more. So let's move on. So I move on actually to the notion that we look at, which is group incentive compatibility with transfers. What I mean by that is that now the difficulty we had in group incentive compatibility is that it was hard to make everybody go in the same direction. Now let's just look at the sum and allow for transfers among the deviating group. And if you use the specification that we have, then with linear quadratic utilities, in fact, the definition that you have looks like this, so it's not very helpful, I guess. But it's a workable definition. And one way to think about it is that it's a definition which says that the contract is going to be okay. It's going to be if you align in some ways the quantities that the agents consume with the externalities that they benefit from. So you want to give an agent, if you give to an agent who has high externalities, a high consumption, then that's going to be fine. He's not going to be willing to exchange with another agent. Okay? So let me give you the two results that we have in the paper. The first result is about what happens when you have a symmetric influence model. So suppose that you have undirected networks. So all the agents have symmetric influence. So if I influences J, then J influences I. Then the result is that if you have that symmetric influence model, then the optimal contract is always going to be group incentive compatible with transfers. So it's not a trivial result, but what it captures is the idea that actually you will then align. If an agent has a higher quantity, it means that he benefits from higher externalities. The problem appears when you have completely non-symmetric situations. So let me look at a class of networks which have very, very non-symmetric structure, directed nested neighborhoods, which means that you have one set of influencers on the top. They influence everybody, but they're not influenced by anyone. Then you have a hierarchy. You have the level 2 who don't influence one, but they influence everybody below, and so on and so forth. Well, in that particular setting, you can show that the optimal contract X star is going to be incentive compatible with without transfers, but if you allow agents to make transfers, then you are going to, I mean, that is very bad in terms of efficiency because you end up being forced to choose a uniform contract for everybody, the same quantity X for everybody. Anything else actually is subject to manipulation by groups of agents. Let me finish here.
Thanks a lot. Next speaker is Ozan.
Oh, sure.
All right, good afternoon everyone, and thanks for having me here. My name is Ozan Candogan. I am actually delighted to give this talk after Francis and Chris, because Chris talked about persuasion, Francis talked about networks. I'm going to talk about persuasion in networks. So I'm going to dive right into the model. This is a theory talk. I will be thinking about an abstract setting where I have an underlying social network. Nodes in this network will correspond to players in a game, and these agents are going to take binary actions. If agent I takes action 0, her payoff is 0. If she takes action 1, her payoff is equal to the state plus a network externality term. So the second term captures the number of agents in my neighborhood who also take action 1. Now the state is distributed according to a known distribution, and it belongs to a subinterval of the reals. And agents do not observe the state prior to taking an action. So in the absence of any further information, agents take action so as to maximize their expected payoffs. We will focus on the problem of an information designer who actually sends informative signals to the agents so as to influence their decisions. In particular, I'm going to assume that the designer commits to a public signaling mechanism. By that I mean everybody observes the same signal. That shares an informative signal S once the state is realized. So it is in the Bayesian persuasion setting that Chris was also working in. So think about a public signal as just a mapping from the state to a signal, so a function f that maps each state t to a signal S. Given the state realization and therefore the signal realization, agents update their posterior beliefs and play a game with slightly different payoffs. The designer tries to choose this mapping between the state and the signal so as to maximize the induced expected activity. So the research question I have here is, what do the optimal public signaling mechanisms look like and how they depend on the network structure? If you want to think about a concrete application, think about agents in a social network. A seller is promoting a product that exhibits local network externalities. The quality of the product is a priori unknown, and the platform can commit to sending informative signals about the product, like through an expert review system, so as to maximize the total number of adopters. It fits into the framework that I'm discussing today. So what do the optimal public signaling mechanisms look like? Given a mechanism, agents play a game of incomplete information. There might be multiple equilibria. Following the literature, if there are multiple equilibria, I'm going to focus on the sender-preferred equilibrium. That is, I'm going to break ties in favor of the equilibria that are most favorable to the designer. But let's try to think about what these equilibria look like. Fix the mechanism, fix the realization of the signal. Agents update their posterior. They basically play a game where the payoffs look like this one. Important thing is that this is a supermodular game. It's a game of strategic complementarities, and it has a largest equilibrium that we are going to exploit. In particular, since I'm focusing on the sender-preferred equilibrium, really, in order to pin down this equilibrium for each signal realization, I need to look at the largest equilibrium of the supermodular game, where the largest possible number of agents end up taking action 1. So what do the largest equilibria of this game look like? Well, that's also easy to characterize. Suppose that the posterior mean is -5. If I have a group of agents, if I have a community of agents in the underlying network, each of which have 5 or more connections within the community, it's an equilibrium for all these agents to take action 1, because they will benefit sufficiently from the network externalities that will outweigh this utility of -5 due to low state, and it will justify their taking action 1. If there are multiple such communities, the largest one will be the set of agents that take action 1 at the equilibrium of this supermodular game. And this object that I'm describing to you actually has a name in graph theory. It is the k-core of the underlying network for k equals to 5. Formally, k-core is the maximal induced subgraph where all nodes in the network have degree at least k. And I can characterize the equilibrium of the supermodular game in terms of the cores of the underlying network. Therefore, I can characterize the sender-preferred equilibrium of the game that I presented in the previous slide in terms of the cores of the network. Why do I care? Well, if it is the case that for any mechanism and any signal realization, the set of agents who take action 1 corresponds to a core of the underlying network, then following a revelation principle type of logic, I can establish that there exists an optimal mechanism where the signal realizations correspond to the cores, and for signal realization k, the agents in the k core of the underlying network find it optimal to take action 1. So I started with a general information design problem where I was trying to figure out an arbitrary mapping from the state to signals. And here what I'm saying is that you can actually substantially restrict the class of mechanisms to focus on. In particular, the set of possible signal realizations should just correspond to the cores of the underlying network. So that is a really nice structure. Because now my information design problem simplifies to the following. I have a set of possible state realizations. All I have to do is to go ahead and partition that such that when the state belongs to the kth partition element, I send out signal k. All agents in the k core find it optimal to take action 1. Right? That's what I need to do. I need to figure out how to partition the set of possible states to partition elements that are associated with different cores. Well, how do I do that? Here's a mathematical formulation. I'm maximizing over partitions such that when the state belongs to the kth partition element, I send signal k. Agents in the k core take action 1. And I get a reward of rk, which is the cardinality of the k core. I can't have arbitrary partitions. At the very least, it has to be the case that when I send signal k, agents in the k core find it optimal to take action 1. That is, the induced posterior mean should be large enough. Now, you can write a formulation of this type always, but there's a fundamental difficulty. How do I solve this problem? The set of partitions to search over is actually very large. To sidestep that difficulty and get and understand the structure of the optimal mechanism, I follow a two-step approach. Step number 1, I'll work with a convex relaxation of this problem. Step number 2, given the optimal solution to this relaxation, I'm going to lift it. I'm going to reverse engineer the optimal mechanism. And the key observation is the following. If you look at a problem of this type, there are really two quantities that matter. The probability with which I send a signal and the induced posterior expectation. So as opposed to optimizing over partitions, I'm going to go ahead and directly optimize over pk, the probabilities, and zk, the induced posterior expectation under the mechanism. Of course, these objects are related. They need to satisfy some constraints, and I'm going to go ahead and impose some constraints. And this is a finite dimensional optimization problem. It's a simple convex program. This is an important distinction, actually. In information design literature, you'll often see some linear programs, etc., written. But when the state is a continuum like the setting I am in, usually these are infinite dimensional optimization problems that are hopeless. Whereas here, I truly have a finite dimensional optimization problem I can solve to characterize the optimal mechanism. And this is a relaxation in the sense that any partition induces a feasible pk-zk tuple, but not vice versa. Turns out, though, that this relaxation is tight, and the proof is constructive. In the paper, I show that you can take an optimal solution to this problem, and using an algorithm I provide, you can construct the optimal partition and the mechanism. And not only that, but also by exploiting the structure of this optimization problem, you can actually show that optimal mechanisms always admit a real nice structure, and a peculiar structure, actually. They always admit a double interval structure. By this, what I mean is the following. You take the set of possible state realizations, and with each signal realization or with each core of the underlying network, you associate up to 2 intervals. For instance, in this example, this is a Facebook subnetwork from the Snap web page. I computed the cores, solved my optimization problem, and with some cores of the network, with 31st core, for instance, the optimal mechanism associates 2 subintervals of the set of states. And whenever the realization of the state is in one of the pink intervals, I send signal 31. Agents in the 31st core end up taking action 1. With some cores, I have a single associated interval. With others, I have 2 associated intervals, but never 3. But because of this double interval structure, it is the case that some agents, will end up taking action 1 for low states, for high states, but not for the medium states, which is quite counterintuitive if you think about that. Right? Agent takes action 1 for low and high states, but not for the medium states. So here's where I stop. This is the teaser for the rest of the results in the paper. Speaking to Dean's point yesterday, I don't actually need to know the network structure to do some of these things. In particular, for large random networks, I show that using only the degree distribution, not the network structure, but using only the degree distribution, I can characterize the asymptotic size of the cores and asymptotically optimal mechanisms. No refined information needed, just the degree distribution. The framework extends to settings where the payoff of the information designer is an increasing step function of the posterior mean, her signals induce. This applies to any finite supermodular games. You don't need binary actions like what I highlighted in the beginning. Similar approach also extends to settings where I'm persuading a single receiver whose type is private. In that setting, the optimal mechanism admits a laminar interval structure which generalizes double intervals. Too difficult to explain in a minute, but basically if there are m private types, the optimal mechanism ends up associating at most m plus 1 intervals with each signal realization. When there is no private information, m is equal to 1, I recover the double interval structure. So the previous result extends quite elegantly. I'm sorry. Thank you very much. I'm sorry for being over time. Thank you very much for your attention.
Hi, everyone. I should do this. Hi, everyone. So my talk is a very different talk than the previous few. So in the last 3 talks, what we had is we had a platform that wanted to send signals or send information to people. And so the people would do what the platform wants them to do. My talk is really the opposite, is how can the platform design something such that people give the platform the information such that the platform can do whatever it wants to do. And it's in the context of rating systems, which are really information systems on these online platforms. So I think most of us have probably interacted with rating systems, but I have this slide up here to show that there really is a very large design space for how we can do rating systems on platforms. Sort of you can modify the question that you ask, the answer choices, how many answer choices, do we ask questions on different dimensions, do you have text? There's really like an extremely large design space, and we need a principled way to think through how do we make decisions to get the information that we want to get. And so that's the first challenge. The second challenge is maybe I just lied to you, and that empirically, a lot of platforms have shown that basically whatever you do, you're going to get the same thing. You're going to get inflated, uninformative ratings where most people are getting the top possible rating most of the time. And so the problem in such a scenario is that that's really bad informationally, no matter how you sort of cut it up, is you get no distinguishing signal from to distinguish maybe the best possible freelancer or the best possible worker, seller, or buyer from the worst possible one. So the point of this talk is these 2 challenges aren't hopeless, that platforms can design the information that you get from people. And really it has 2 parts. The first part is an empirical part, is how does change in the design change in the information that you're getting? How does changing the rating system change the responses people are giving? And so this is the experimental part of the paper, which is in which we look at, can you actually change the rating question that you get, the question that you ask people, and do you get different responses? Neither Ramesh and I are behavioralists, but we think that we sort of came up with or found a nice solution that seems to deflate ratings on online platforms. But even if you have something, even if you have sort of a lever you can pull to change the ratings that you're getting, to change the information, then you're left with really a theory problem, which is how do you connect the ratings that you're getting or the information that you're getting to something that you really care about as a platform? So whatever the objective of the platform is, and this is really a theory problem. So here, what we look at is how does the feedback distribution that you're getting of ratings affect how quickly you learn about participants? I'm going to focus on the first question, the experimental part for most of the paper, for most of this talk, and then I'll sort of see how we apply it at the very end. Okay, so we have an experiment on a large online labor market that will remain nameless. So the status quo on this online market is that clients hire freelancers and then rate them at the end of the contract. And sort of the feedback form is pretty long, but the status quo includes a numeric rating already that's 0 to 10. And of course, like every other platform, it's inflated with like averages, I think, over 8.5 out of 10. So the challenge is, can we add a new question to this form that induces non-inflated ratings? And So the experiment design is exactly what you would expect, is we add an additional question to the private feedback part of the form, so freelancers never get to see the answer for this question. And we add 6 different questions, so we have 6 treatment cells, and a client is allocated to a single treatment cell throughout the experiment period. So if a client closes 10 jobs during the period, they'll see the same question the entire time. And then we observe all ratings over a 3-month period, which is about 180,000 jobs that were closed. So the first treatment group, which is sort of a pseudo-control, is adding the status quo on many of these platforms. Is we just added a new question that was phrased differently than the existing questions. And it's just, how would you rate this freelancer overall? And then 0 to 5 stars. The behavioral intervention that we wanted to test is many variations of the second treatment that I have, which is we asked the same exact question, how would you rate this freelancer overall? But then the answer choices were adjectives, so they range from terrible, but then sort of we positive skewed the adjectives. So the equivalent of a 2 out of 5 would be good. The equivalent of a 3 out of 5, which basically no one gets, is great. And then 5 out of 5 is the best freelancer I could imagine, the best possible freelancer. And we wanted to see is can maybe raters don't want to like insult their freelancers or insult the people they're rating, but by giving them low ratings. But maybe if we reinterpret it for them, they'll give us more dispersed ratings. The rest of the treatment cells are variations on this idea. Okay, so what do we see? So this pseudo-control of adding this new numeric question results in exactly what you would expect from the prior ratings literature. You see over 80% of people are getting the top possible rating, and then there's like a very slight J-curve where there's another tiny peak at a 0, and then basically nothing in the middle. All the additional treatments result in radically more dispersed ratings. So here, the less than 35.8%, so all of these is less than 35.8, which is, so very few people are now getting the top possible rating. If you're interested, the p-value here is like 10 to the negative 100. It's ridiculous. And however, so we have some evidence that we can provide deflated ratings from just all we have to do is an intervention of positive skewing them. Unfortunately, I haven't told you how informative this is. A possible behavioral tick that's consistent with this data is that like 90% of people don't like reading, and so they'll pick a random word.
So in the treatments, do you still have the numeric rating, or is it replaced by the words?
Yes. So we have all the existing form is still there. So we still have the existing 0 to 10, but then in this new question we just have the words plus this. In this specific treatment cell, there's 0 to 5. Okay, so I haven't told you yet that they're informative. I'm gonna try to do one pass of it being informative, and then I'll jump into the theory, which tells you like the right metric of informativeness that you might care about. Okay, so why we don't think this is most people not liking to read is that we can exploit the fact that on this platform in question, the same client tends to hire the same freelancer for multiple jobs over a period and over like a few months, and they close each of those jobs, so we might see multiple ratings. In particular, we'll see what we can do is we can look at the first rating that a client gives a freelancer in this experimental period, and then we can just observe, are they ever hired again? And what we should see is that clients who give the freelancer a 0, saying that they're definitely not worth hiring or terrible, should not rehire them. And then people who give them fantastic ratings should, freelancers who give clients fantastic ratings should probably rehire them at a higher rate than normal. That is exactly what we see. And in particular, you can also see that these verbal positive skewed ratings are providing more information at the very top. So sort of these are hard to interpret, but what's going on is if you get a numeric 5, then you're about 20% more likely than the average freelancer to get rehired. But if you get the top possible rating in one of these like verbal scales, you're about 40 to 50% more likely than the average freelancer to get rehired. Okay, so this is again some evidence of that we're providing informativeness, but if you're someone like me, you're not really satisfied by these metrics. What you really want is, okay, what is the platform actually learning toward the things that it cares about? So I'm going to blaze through the theory. This is mostly an advertisement for the paper and a sort of a follow-on paper. So what we're going to assume is, in the theory, that we have a joint distribution of the ratings people receive and their true quality. And then we make up some model in which sellers are accumulating ratings according to this joint distribution, and then the platform just estimates their rating and then a ranking. And then you can derive large deviation rates for how quickly this estimated ranking converges to the true ranking that you care about. In a follow-on paper, in a binary setting, we say, what if you don't just care about like the ranking uniformly, but maybe you care about parts of the ranking more? But I'll not get into that. Okay, so to apply that to our experiment, we need to have estimates of the true quality because we need to estimate this joint distribution. I'm again going to skip how we estimated true quality. And then I'm going to say, but once we do that, once we have this rows, we can just compare scales by their induced large deviation learning rates. And you can indeed see that, so one, you get a number now that's saying this is how much better this scale is than other scales. And then see that it matters in a simulated market for how quickly you're converging to the true, sort of estimating the true ranking. And I'll end with my takeaway slide again.
Thank you. Last speaker is Michael.
Okay, well, I think I have about -5 minutes to get us out of here with time. So I'll try to talk very fast. I appreciate the opportunity to present this work, and I appreciate you guys all for sticking around. Let's see if this works. It does not. Okay, so I want to be talking about mechanism design with correlated valuations, efficient methods for revenue maximization. So a common assumption in mechanism or auction design is that bidder valuations are independent. This holds in almost no settings of interest. And a more realistic assumption is that bidder valuations are drawn from some joint distribution. And if you have this joint distribution and you know it, you can do some pretty incredible things with mechanism design. In fact, private information doesn't have any value anymore. With probability 1, private information loses all value under this correlated setting. That's assuming you're okay with Bayesian mechanisms, which I am, and I hope you guys are as well. But in the real world, we don't really know this distribution. We might have some fuzzy idea of what it looks like, or more realistically, we might be able to interact with bidders over some kind of repeated setting and learn this distribution. But the question is, how do we design mechanisms when we are trying to learn this correlated distribution? So what I'm going to present is an automated mechanism design procedure that is both computationally and sample efficient for jointly maximizing revenue and social welfare when there is sufficient correlation. And so these are a preview of the simulation results here in case I don't get to them. All right. So just for the sake of exposition, we're going to assume that there's a monopolistic seller with one item. There's going to be a single bidder with type theta drawn from a discrete distribution of types, and his valuation is going to be V of theta. And then there's going to be an external signal that is correlated with his type. So this is going to play the role of potentially other bidders who have correlated valuations, but without all the complications of having actual other people. This will provide the side channel into this bidder's information. For the purpose of this talk, I'm going to assume this external signal is binary, just thumbs up or thumbs down. But in the paper, it can be an arbitrary, discrete external signal. And so we all know what mechanisms are. I'm going to use quasi-linear utility, which is important for these kinds of mechanisms. And once we have this, we can design the optimal mechanism using a linear program where we pick our choice of individual rationality and incentive compatibility. If you want to extract full surplus, you're going to have to choose the Bayesian mechanisms. And then we have an allocation constraint. So intuitively, what's going on here? Well, I can encode all the information of the problem on this graph. A type is a dot on this graph. The horizontal axis can be considered a one simplex, which is the beliefs over the external signal that type the bidder has. When there's no correlation, types are all vertically aligned, meaning they all have the same beliefs over the external signal. I can also encode different marginal probabilities using different size dots here. And in this case, the optimal mechanism would just be a take it or leave it offer, where we would sell the item at 2. All of the dots above the line 2 would buy the item. Anybody below would not. If you have correlation, though, and we use a Bayesian mechanism, well, then these dots are no longer vertically aligned. And we can, instead of making a take it or leave it offer a take it or leave it lottery. This line indicates that the lottery has charges a price of 5 when thumbs up is seen, and a price of 0 when thumbs down is seen, which means that anywhere your expected payment is anywhere along this line. And this is how we, okay, so I have to end quickly because the battery's running out. So this is how you extract full surplus. This is how you get rid of the value of private information, is that in expectation, each of these guys pays their full value, and it doesn't matter what they report, right? And it turns out we don't need these dots to be very, far separated. They can be quite close together, and we just end up with lotteries with extreme payments, which you may or may not be comfortable with, but we still, in expectation, extract full surplus. So this is the Kramer-McLean result from 1985. If you're not familiar with it, it's a wonderful paper. So what if we have access to samples now and there is sufficient correlation? And why am I saying that we need sufficient correlation? Well, in a paper in Amos 2017, we showed that if you don't have sufficient correlation, learning is impossible here, if you have a continuous set of possible distributions you're trying to learn from. The Kramer-McLean result of arbitrary correlation, getting rid of the value of private information, is not true when you're trying to learn from a continuous set of distributions, or even just an countably infinite set of distributions. So what do we actually observe? We don't observe the true distribution. We observe these orange dots, which is a reported value and external signal. And the relative sizes of these dots might indicate the relative times we see that particular sample. So given these dots, I can estimate the distribution, maybe this blue dot here, and I'll have some interval under which this belief is consistent with that estimate, right? Some kind of confidence interval, if you will, around this. I'm going to call these confidence intervals an epsilon consistent set of distributions, which just means that there's a set under which the true distribution is in that set with high probability. So once I do this, well, I can design the naive mechanism where I just optimize according to my expected distribution, my expected distribution. But if the true distribution looks like this, which is in this consistent set, then for this guy down up here, I don't really lose that much revenue, but I lose a little bit, not a big deal. But this guy down here no longer participates because it's not individually rational anymore. So the obvious solution to this is to lower this line a little bit. When you lower this line, you lose expected revenue, but you never end up in this catastrophic situation where people choose not to participate. So it turns out we can design these mechanisms by modifying the linear program. We end up with an infinite set of constraints, but we use a constraint generation approach to show that we can solve this in polynomial time. So great. And the question is, how do they perform? Well, we need sufficient correlation, and it's not Pearson correlation. The relevant condition is around the kind of a sufficient linear separation of these conditional distributions. So if we have 3 possible external signals, and this is the 2 simplex, then that condition states that these conditional distributions are sufficiently far away from the convex set of other conditional distributions. So it's this notion of you sufficiently satisfy the original Kramer-McLean condition, not just satisfy it, but satisfy it by enough. If we have this condition, we can show that we can compute a nearly optimal mechanism with a polynomial number of samples. It's not a small polynomial, but at least is a polynomial. Okay, so we use simulated data to evaluate this approach. It's a discretized bivariate normal distribution. We sample from the distribution some amount of times. We use Bayesian methods to estimate the distribution. We can calculate empirical confidence intervals, and then we can vary correlation and other things. And what we see here is that if you take if you just look at the ex post, just realized that some of my slides didn't end up in here. It's a little shorter than I thought. If you take just an ex post mechanism and look at the optimal ex post mechanism given your estimate of the distribution, you never do all that well. You actually barely do any better than just ignoring the correlation altogether. If you take a Bayesian mechanism and just kind of naively optimize for it, then you end up dramatically overfitting. The error bars around this Bayesian mechanism are just gigantic because it's effectively overfitting. And then our approach smoothly and converges to the full surplus extraction and does significantly better than the other two approaches. And consistent with our results about the degree of correlation being important for learning, we show that, or we confirm that the more correlated the setting, the quicker it is to learn these mechanisms. All right, so there are other applications and research directions, but I'm happy to talk about those offline. So thanks very much for staying and listening, and I'm happy to take any questions afterwards.
Thank you very much to all the speakers. It was very interesting and very disciplined, so that was great. The delay in time was only because of the technicalities between the talks. So have a very nice evening, and see you all tomorrow for the last day of the workshop. Bye-bye.